The last main topic we want to talk about is polarization. That refers to the exact way that the electric field is oscillating. You'll notice in this drawing, the electric field is drawn as if it's moving up and down along the y-axis. It's increasing and decreasing along the y-axis. So the electric field always points in the y direction, but it could be positive or negative. If I drew a cross-sectional picture from the front, I would see the electric field varying from large and positive to 0 to large and negative back to 0. And the magnetic field goes perpendicular. So the magnetic field would be here in the z direction, and this is showing the light coming out at me in the x direction. We call this plane that the electric field is in the plane of oscillation. So it's formed by the direction of the electric field and the direction the light is propagating. And whatever direction that motion of the electric field is, that's called the direction of the polarization. Now, in regular light that we get from the sun, the light is polarized in all sorts of different directions, randomly distributed in all different ways. So as light comes towards us, it can go up and down this way, sideways this direction, side to side there, any particular direction we like. What's more, the phases of these different bits of light are not all together. So that's called randomly polarized or unpolarized light. However, there are materials that are able to selectively absorb and transmit just one polarization direction. And those are called polarizers. Let's talk about them for a moment. Let's briefly talk about reflections. You already know that metals tend to reflect. And the reason for that is that their electrons are free to move. So I have an electric wave, an electromagnetic wave coming in, and it oscillates up and down like this. When it hits an electron, that electron is going to start moving opposite. It's going to move up when it's pushed down and down when it's pushed up. But that motion of the electron produces a new wave which cancels out this one in the forward direction and creates a new one going back the other way. End result, we go from having a wave propagating to the right to a reflection propagating to the left. But in order for that to be able to happen, this electron has to be able to move up and down. Well, if I've got a fairly long wavelength, like a microwave, I can make a grid that looks like this. Now, a lot of people think a grid like that would let the up and down light pass through, and the side-to-side light would get blocked. But that's actually backwards. A grid like this conducts in the up and down direction, and does not conduct in the side-to-side direction. As a result, microwaves would be reflected if they're going up and down, where the wire can conduct the electricity. But if it's going side to side across these blades so that it can't conduct, then the light, microwave rays, go straight through it. Something very similar can be done with long organic molecules in a polarizing filter. They absorb along one direction, where it can actually move their electrons, and just transmit along the other direction. So, if I start with unpolarized light coming in towards such a polarizer, when it hits the polarizer, the light that's going perpendicular to the polarizer gets absorbed and is not sent through. But the light traveling parallel to the polarizing axis goes straight through. Now you might look at that and look back here at this unpolarized light and think, Well, only a very small amount of the light is perfectly aligned along that polarizing axis. That's true. But remember, light is made up of electromagnetic fields, and those fields are vectors. In other words, if I have a field, or if I have a light wave, where the electric field is propagating along this direction, and the polarization axis of a filter through which it's passing is polarized that way, then we just take a component of the electric field that is parallel to the axis. That component is going to be E times the cosine of theta, where theta is the angle between those two vectors, between the polarizing axis and the axis of the electric field. If we then do that, we take all the possible cosine of thetas and average them out over this entire situation. What we find is that when we go from unpolarized light through a polarizer, exactly half of the light gets through. So if I have an intensity I naught here, the intensity here is 1/2 I naught.